Well, hope we're doing well. 7.5 is, I'm sure you've realized by now, basically just a review section of the previous four, also folding in U sub, and basically it's a review section of everything that you've learned about integration thus far and the methods by which we can sort of change the form of the integrand. But it's called strategies of integration rather than techniques of integration because you have to have sort of a strategic perspective on what's going on and sort of, how do you walk through those questions that you ask yourselves and stuff like that. I figured that there was no better way to do that than to basically show you the tests that I've given in the past. And like I said, I've usually given tests where I basically on each page gave two integrals and ask them to pick one of them. And the reason I do that is because, obviously there's a certain amount of being able to see it that's sort of, important for all of this. So let's go ahead and jump right in. I'm basically have printed out two of each page, and I'm just going to work on one of them per page. So let's say I chose this one on the left. Now, it doesn't have a form that's trigonometric, so it's not going to be a trigonometric integral. It's not of the form where it looks like I'm going to plug in some trigonometry in order to make use of the trigonometric identities in order to take a binomial and create a monomial out of it or whatever. So it's not going to be trig sub. It's not an irrational structure, so it's not going to be partial fractions. This one winds up being just straight up parts. Now remember, you need to designate your u and you need to designate your dv. In this one, basically your u has to be natural log y, and the reason is because if you put natural log y right here, natural log y in and itself is a parts problem. And so basically, the derivative of natural log y, but natural log y's antiderivative would require a separate integration problem involving parts. So we put natural log y here, and we put y dy here. Now usually we put the polynomial term here, the polynomial factor here, because we want it to come down in degree. This obviously goes up in degree, but that going up in degree is going to be cut by this 1 over y when you combine these two in the integral. Now remember that this is your u dv, and you need your uv, and I'm going to write it like this just to make it nice and pretty, minus v du. Well, I'm going to pull the 1/2 out in front, and then 1 over y and y squared simplify to y dy. Now that gives us 1/2 y squared natural log y. And y, of course, we know how it anti-differentiates. Not only is it rather simple, we've actually just done it. And it winds up being that. Now, I mean, you can make it, a little bit prettier, of course, by pulling out a 1/2 y squared. And then you would just get natural log y minus 1/2 plus c or something like that. But you are more than welcome to leave it in that form right there. Now, let's go ahead and do the other one on that same sheet. Let's say we skip that one and we're going to opt for this one. Okay, well, that's also going to be parts for precisely the same reason that the other one was. Basically, by process of elimination, there's no reason to do trig sub because there's nothing that requires that type of the change of form. It's not already trigonometry, so it's not going to be using any of the identities from the trigonometric integrals. It's not in a rational form, and therefore I don't need to do partial fractions. Basically, it has to be parts. Now, by rules of exponents, you need to remember that e to the 5t is basically, you can change the form, and you might want to at least entertain the possibility that it would be a good idea to do that. But basically the only way that that actually happens is it becomes e to the t to the fifth, or e to the fifth to the t, and neither of those are really all that helpful. So I'm just going to have to deal with e to the 5t. Okay. Now, I know that this is, unlike my natural log, my exponential, I do know how to integrate that. So my u here is going to be sort of straightforward t squared, and my dv is going to be e to the 5t dt. Now that means that when I anti-differentiate it, I need 1/5 e to the 5t, and my du right here is 2t dt. That means that if I have this, I have 1/5 t squared e to the 5t minus, and you have a 2 and you have a 1/5 here that you can pull both of those out in front of the integral before stating it as, t e to the 5t dt. Now, what you're going to need to do is another round of parts with this one. So this integrand is going to be divided up into parts again, and you want to go ahead and whatever portion of it you designated as u last time, you designate as u this time, and it just becomes dt. Now my dv is again e to the 5t dt, which we did this last time. Gives us 1/5 e to the 5t when I anti-differentiate. Now remember that you have to basically this is going to become a difference, and we need to put parentheses or brackets or something around it to ensure that we are going to distribute this negative. So we have 1/5 t squared e to the 5t minus 2/5, and of course I need uv, so that's going to be 1/5 t e to the 5t minus 1/5 integral e to the 5t dt. Now this, we finally arrived at an integral that is integrable, and so let's go ahead and simplify real quick before we integrate. Actually, we can simplify and integrate in the same step. So negative 2/25 t e to the 5t plus 2/25, and what's going to happen here is this is going to become, again, this is the third time we've done it, 1/5 e to the 5t plus c. So all we really need to do now is just simplify this by combining those factors as the coefficient, and I get 1/5 t squared e to the 5t minus 2/25t e to the 5t plus 2/125 e to the 5t plus c. And if you're looking to be all nice and tidy, you can of course bring out a 1/5 e to the 5t and make it, t squared minus 2/5 t plus 2/25 plus c. But it's unnecessary, simply because remember that you need things in the form that's going to be most useful for you. Now this one obviously took a few more steps than the other one, so you might think that the other one is quote-unquote easier. Well, only if you see it, right? Only if you can actually see it is it easier, but both were parts, both were pretty manageable. So let's go ahead and move on to the next page. I gave my students a choice on this, so let's go ahead and again pick the first one and get going on it. Now, what I need to do is I need to discern what that is. Now, it's not trig. It probably is not going to be trig sub, because when I'm looking at that denominator and I'm thinking, that probably factors. And the reason that I know it factors is I know that this factors, right? And this is just the same coefficients in reverse. So if this factors into x plus 2 and x plus 1, then this denominator is going to factor, right? Then 2x squared plus 3x plus 1 factors into 2x plus 1 and x plus 1. Because no matter where the 2 is, you're still going to get it. It's still going to become involved in creating that middle term, because the middle term is of course the opposite, and I mean the outside and the inside products added together. So basically, what happens here is I recognize that I have something that needs to be pulled apart according to partial fractions. And I have a over 2x plus 1 and b over x plus 1, and predictably we're going to go ahead and multiply through by both of those factors in the denominator to get rid of all of the denominators. They're simple linears, and so I'm going to be able to use the Heaviside method and plug in convenient values to find a and b. So so if x is equal to -1, then we have 1 over here. The a falls out. This becomes -2 plus 1, or -b. So b is equal to -1. Now, what we need to do next is we need to go ahead and let x, and if x, let x, whatever, let x equal to -1/2. Now, we didn't do many where that was required, and, fractions, not fun sometimes, but you're big bad calculus students, so you should be able to deal with it. Obviously, -1/2 is going to make sorry about that. Something about my document camera glitched, and so let's just go ahead and start over on this problem. We're doing this one now. We've already established that this factors into 2x plus 1 and x plus 1, and that we want a over 2x plus 1 and b over the x plus 1. Now that allows us to use the Heaviside method, because both of those factors are linear. So we're going to let x is equal to -1. That's going to be 1 is equal to a times 1. Okay. No, we need -1. Sorry, we need x is equal to -1. So that's actually going to be b. If we let x is equal to -1, that's going to be 1. And when we plug in, -1 plus 2 is 1. And then -1 up here is b -1. So b is equal to -1. So if we let x equal to -1/2, which is going to get rid of this one, this is going to be 3/2 is equal to a times 1/2, or a is equal to 3. Okay, so we've done our decomp, and that tells us that our integral is going to be 3 over 2x plus 1 minus 1 over x plus 1 dx. Well, this isn't very difficult at all. This first one becomes 3 2x plus 1 dx, right? And this one becomes dx over x plus 1. The only thing that this one needs is a 2 up here, which of course needs to be compensated with a 2 out in front, and we're going to wind up with 3/2 natural log absolute value of 2x plus 1 minus the natural log of x plus 1 plus c. Okay. Now, we need to move on to the next one. And we're going to be doing this one and not that one. Okay. Well, this one becomes, when we factor, x and x squared plus 1. Okay, can't use the Heaviside method, but it's really not all that difficult, especially since the linear is simply x. So we have bx plus c over x squared plus 1. We're going to go ahead and let x is equal to -1. Oh, whoops. Let's go ahead and turn it into, sorry, getting ahead of myself. Bx plus c times x, and let's let x is equal to 0, right? X is equal to 0 because I want to zero that out. So this becomes 1, and a times 1, and that gives us, a is equal to 1. That's great. Now we're going to have to make recourse to coefficient comparison, or we're going to have to plug in random values and get two equations in terms of B and C. I like coefficient comparison, so we're just going to go ahead and multiply things out. This just becomes x squared plus 1 because a is 1, and this becomes bx squared plus cx. Now the only thing that really needs to be combined is b plus 1 plus cx plus 1. Put it in descending order, and I get 0x squared plus x plus 1 over here. Now, that means that b plus 1 is equal to 0, and therefore b is equal to negative 1. And c, of course, is equal to 1. That means that this up here is 1 over x plus 1 minus x over x squared plus 1. And I did it 1 minus x because the b value was negative and the c value was positive. So I just, instead of saying negative x plus 1, I just flipped it around. Now, what needs to happen here is, of course, the integral needs to be rewritten as this. Now that numerator is really unhelpful for this denominator. It needs to either be a constant or a first degree linear. And so what we're going to do is we're going to separate it. Now this first one becomes dx over x. This second one becomes dx over x squared plus 1. This next one becomes x dx over x squared plus 1. And in order to actually make the u substitution for natural log possible, we need the 2 and therefore a negative 1/2 right here. So now that we have all three of these in forms that we actually recognize, this is natural log of absolute value of x. The second one is arctan of x. This third one is the natural log of x squared plus 1. We're not using absolute value bars because x squared plus 1 is always positive, so it would just be redundant. But this is our decomp, and as a result, this is our integral. Now, let's go ahead and move on to the next page, and we have a choice between these two. Now, they are rational, but they're rational in structure, but they're not going to be decomp problems, right? They're not originally trigonometric, but trigonometry might help. They don't look like parts, although I'm not quite sure. I haven't looked at them long enough to determine whether one or both of them can be done by parts. But let's just go ahead and concentrate on this one for now. Now we notice that we have a binomial underneath the radical, and that is usually an indication that trig sub can actually help us out. Now if it's a binomial and it's addition, we're going to be using the tangent squared theta plus 1 is equal to secant squared theta identity. So we want that x to be equal to tangent theta. By the way, that means that tangent theta is equal to x over 1. That's going to help with our triangle that we set up here in just a moment. My dx then is secant squared theta d theta. Okay, well let's go ahead and pop all this into the integral. And we notice in the numerator, let's go ahead and put our dx in the numerator. Dx is secant squared theta d theta. And x squared is tangent squared theta. And then this was 1 plus tangent squared theta. Okay, well that simplifies. Let's see, secant squared theta here in the numerator still. Tangent squared in the denominator. Now underneath the radical that becomes secant squared, which then just becomes secant theta. That secant cancels out with one of those secants in the numerator, and now I'm a little bit confused because I have secant and tangent and I know that they're related by Pythagorean, but tangent's in the denominator and that's not really all that helpful for me. So what I'm going to do is, when all else fails, turn it into sine and cosine, right? And what happens here is this winds up becoming, when you sort of flip it all around, it winds up being cosine theta d theta over sine squared theta. Well, that's a little bit more helpful because then we can just use u sub for basically u sub for a power rule. If we rewrite it as sine theta to the -2, and then this is my u to the -2, and this is my du right here. Okay, well that basically becomes -1 over sine theta plus c, which is of course negative cosecant theta plus c. All right, well, I've integrated. I've gotten it to an integration answer involving theta. Now I need to change it back to my original variable. Okay, so let's go ahead and set up that triangle. Okay, now originally it was x over 1 tangent, right? Which makes this right here the 1 plus x squared, which shouldn't surprise any of us. Now cosecant is the hypotenuse over the opposite because it's the reciprocal of sine, right? And so what I have here is negative 1 plus x squared over x plus c. And if you want to confirm that, of course, you can take the derivative of it, and you actually do wind up getting the original integrand. All right, well, let's go ahead and move on to the next one. Okay, we're going to do the other one on this page. Alrighty, now that one also looks a whole lot like it would benefit from trig sub, but it's maybe a little more complicated in the fact that it's a difference and it's not 1, it's 9. But sine and cosine are usually kind of our comfort zone. So I know some people might actually opt for this one simply because it's sine and cosine, and it's a little bit easier to deal with those than secant and tangent. It's just kind of like a comfort zone sort of thing. So we know that we need x squared to be 9 sine squared. So x simply needs to be 3 sine theta. And that means that, sine theta is equal to x over 3, and we know that dx is equal to 3 cosine theta d theta. Okay, well, I have pretty much everything that I need at this point. I'm going to go ahead and go over here so I don't, limit myself in terms of space. In the numerator, I have x squared, and I'm going to go ahead and put my dx up in that numerator as well. So I have 9 sine squared theta times 3 cosine theta d theta. Down in this radical, I have 9 minus 9 sine squared theta. Now, the whole point is for that to become 9 cosine squared. And the square root of that, of course, is 3 cosine theta. Well, that just happens to cancel with that. And I'm left with 9 sine squared theta d theta. Okay, well, this doesn't have a cosine, so I'm not going to do u sub, but what I am going to be able to do is I'm going to be able to use my power reducing, okay? And if you don't remember power reducing, it comes from the cosine, let's call it theta, since we're actually using theta in this particular one. Cosine of 2 theta is, of course, cosine squared minus sine squared. But that actually winds up being 1 minus 2 sine squared theta. And all I have to do in order to get my power reducing formula, or my ID, is simply to solve for sine squared, right? So I have 1 minus cosine 2 theta, and then sine squared theta is equal to 1 minus cosine 2 theta over 2, okay? So that was our sort of little aside. Well, I don't need the over 2 inside the integrand, so I'm going to go ahead and pop that out as a 9/2, and I have 1 minus cosine 2 theta d theta. Well, that becomes 9/2 theta minus, okay, well, cosine 2 theta is the derivative of 1/2 sine 2 theta. Now, sine 2 theta that doesn't do us much good if our triangle is set up with theta, but we also know that our double angle identity makes this sine theta cosine theta, because sine 2 theta is 2 sine theta cosine theta, and the leading 2 will cancel with the 1/2. Now let's go ahead and set up our triangle so that we can go ahead and plug the stuff in here. Let's go ahead and so let's go ahead and put it right here. It's just never enough room. Too many things going on. So let's go ahead, and here is our triangle. Remember that the original for theta was x over 3. That makes this adjacent side 9 minus x squared. Okay. That means that when we're dealing with this, I know that theta, okay, needs to basically become arc sine of x over 3. So this becomes arc sine of x over 3. And then we have minus 9/2. And sine, we already know, x over 3. And cosine should be this radical over 3, so 9 minus x squared over 3 plus c. Sorry, getting a little close to my triangle. And we therefore are going to simplify this down to 9/2 arc sine x over 3. These 3's will cancel with that 9 and will give us 1/2 x radical 9 minus x squared plus c. And that is my integral. Okay. Okay, let's go ahead and look at the next page. Actually, I'm going to go ahead and end this video, and we'll start up the next video on this page, and then we'll sort of at least try to get through